Hello and welcome to another episode here at toysandphysics.com. Today we have an interesting problem to solve and analyze. And well, before starting that, I just want to share that we might have some background noise today. I have my daughter here with me, so she'll may jump in eventually. She's 1.5 years old, so just so you know, it's going to be fun. It's going to be interesting. It's also going to be challenging. Okay, so our problem here, it's we have two vehicles here, a motorcycle and a car, and both are racing, right? So we are given some initial conditions. We're going to go into more details later into that, but for now, just want to paint the main picture of what's going on here. And we have a motorcycle and a sports car that both start from rest. That means initial velocity equals 0. And of course, in a race, they start from the same spot, right? They start at the same X position. We're going to use the X-axis for simplicity, moving along the positive direction, right? That's to the right. So that's what I have represented here. Now, the problem statement says that initially when they start racing, the motorcycle takes the lead. But there's a point in time where the motorcycle reaches its top speed and then starts or stops accelerating, and acceleration goes down to 0. So there's one from beginning to a certain point in time, the motorcycle it's accelerating and then it's not, right? But then it continues moving along a straight line, and eventually the car, which still is developing speed, still accelerating, reaches the motorcycle and wins the race. So that's kind of the situation we have in front of us, and we want to analyze a bit more in detail the situation so that we can know when is that the car reaches the motorcycle, right? So that's what we have in our second slide here, and I kind of created this short animation which is in slow motion. That's what it will help us to make a better analysis of what's going on. So like I said, we're given some initial conditions with some numbers here, right? And the acceleration of the motorcycle from... There she is. Like I said, there she is. So the motorcycle starts accelerating at 8.4 meters per second square from here to here. At this point in time, it stops accelerating because it reaches its top speed, and then it just goes at constant speed, and also constant acceleration, because 0 acceleration is also constant acceleration. So that's important to notice as well. Okay, so from here to here, the speed it has is this, right? 58.8 meters per second. And then same thing for the car. We have a car that starts from rest. Eventually it reaches 106 meters per second from here to somewhere, to some spot in space and time. But it's doing it an acceleration of 5.6 meters per second squared. That's pretty much everything that we are given. Of course, we also know that both initial velocity for the car and the motorcycle, it's 0, and that they start from the same spot, right? So that's pretty much it. I already explained the situation of the problem, the problem statement. If you want to kind of give it a try and see if there's something you can do with it, you can by all means do it. You can stop the video, pause the video right now, and then come back once you've finished. Or if you want to learn kind of the way I approach this and follow along, then just continue to watch the video, right? But what I have developed here, what I have created here, which I think will help us to solve this, it's that we can tell that there's a distance, there's an amount of distance, right, a displacement at which both the car and the motorcycle share the same spot on, not the same spot, but the same x position, or the same position along an x-axis, right? And like I said, also there's a time, there's a spot here that that's when the motorcycle reaches its stop speed. In that spot, I will say it's xm1, right? So here's when the motorcycle stops accelerating, and from here to here, it goes at constant velocity and constant acceleration, zero, that's zero, until the car reaches the motorcycle, right? So I think that if we can kind of express equations in terms of these positions and times, and then this position and time for the car, we can eventually know this. This is the time that the car and the motorcycle will share the same x position. This is when we want to. This is when both vehicles share the same x position, and that's when we want to. That's the time we want to investigate, right? So let's get into it. Okay, so this is where the magic happens. This is the sheet of paper that I used to solve this problem. Hopefully you won't get confused. I was trying to follow the layout once I finished and discovered that it could be quite confusing, right? But hopefully it's not. Hopefully you'll find it useful, you'll find it friendly, and well, let's get into it. Like I said, excuse me, like I said, you already saw the animation, so what I just did here was to recreate that on this piece of paper here, with pretty much the same information, same nomenclature, same everything, trying to make it everything the same so you won't get confused. But eventually, like I said, we just want to know, when does the car reach the motorcycle? And the answer to that, if you want a short version of this, it's when both are here, right? That's kind of the answer to this. Now, another interesting question would be, okay, when is that both of them are here? And like I said, I just put the same conditions, the same numbers here, and from there we're going to start developing the math that involves and will help us to solve this problem, right? So again, we have the car, we have the motorcycle. So let's get started with what we know. And by the way, first of all, just wanted to highlight, I already mentioned that, but it's important to highlight that both vehicles start from rest. That means that the initial velocity goes to zero. That doesn't mean that the initial position is zero, but I just want to simplify the math that we are going to do and be doing here. So for that, we're going to make this initial position for both as well equal to zero. Okay, so that's kind of arbitrary, but it's something that will help me and will help us to simplify the problem and work with an easier set of equations, right? So let's first go to what we know, and what we do know is the initial velocity of both the motorcycle and the car. That's zero. We already saw that here. Also, the same thing for the initial position. The acceleration of the motorcycle, and here's a difference that I included that it's not on the previous animation. I just labeled this M1 just to make it different from this, to kind of emphasize that's the acceleration of the motorcycle during this initial displacement here, right? But eventually we know that once it's at xm1, that is here, that acceleration becomes am2, and it's zero. It goes zero when the motorcycle it's at xm1, right? So that's something important that I wanted to mention because it's a difference from what we already had. Okay, now we have the velocity for the motorcycle, which is 58.8 meters per second. We know the car's acceleration, which is 5.6 meters per second square, and also that at some point in time it will develop its maximum speed, which is 106 meters per second. Okay, so those are the initial conditions. Those maybe not the initial condition, that's not the proper way to say it, but that's the data we're given to solve this problem, right? So let's start developing it. Like I said, I wanted to make sure that I kind of created the logic to start analyzing this problem from the right angle. And for that, I think it's a great starting point if we can investigate, if we can know the position values of like for instance in this case xc, because that's going to help us to once we know other data and other information, we can also know the TC, which is actually what we're looking for, right? The timing for the car to reach this spot in the x-axis, right? So we know that xc equals xm1 plus xm2 because that's pretty much the same distance that both vehicles go until they are at the same x position, not necessarily the same spot because two bodies could not do that right at the same time. But you understand what I'm saying here. So this is the initial equation that I'm going to build, and from here I'm going to establish a set of equations that we already saw in previous videos and in the lessons at toysandphysics.com, which by the way you can find more information there if you want to know. And well, let's start for the car. Let's start with the car. We know there's the second basic equation. That's what this parenthesis means here. The second basic equation that's at toysandphysics.com says that the final position for any particle with constant acceleration, which is our case here, can be found if you know its initial position, its initial velocity, then you multiply that by the time, you add those two up, and then you also add this quantity here, which is the acceleration of that particle moving and the time it takes for the car, for that particle to reach that position squared, and then you divide that by 2. So just in simple terms, there's an equation that we I would say found or derived from or derived, I'm not sure how to pronounce that, but we found this equation. It's a general equation from constant acceleration situations that you can use. So if we use this, we can pretty much know the final position for the car. And just doing that, and by the way, we're going to be using this equation a lot for the car. We know that xc, which is the final position for the car, xc equals initial position, which is 0. We established that here. The initial velocity as well goes to 0, so this term is 0 as well. And it's equal to 1/2 of the acceleration of the car multiplied by the time it takes for the car to reach this final spot, and that time is squared, right? So that's kind of our final equation for the car. So we already know this side of this main equation that we're going to be working with. 1/2 AC TC squared. Okay, that's the main thing. If we keep scrolling down, yep, there it is. We can do the same thing for the motorcycle. Now, before doing that, we have to find the time, because we can do that. Actually, we have everything we need to do that. We can start evaluating the time it takes for the motorcycle to go from here to here. And we can do that because again, there's one equation, basic equation, the first basic equation that we have at toysandphysics.com. We developed that there's a section on the page that you can, on the site, and the page of motion along a straight line, you can find that procedure. But we determined that pretty much the final velocity for an object moving with constant acceleration can be found with this equation here. So again, we have the initial velocity, which goes down to 0, and we can say that the final velocity for the motorcycle, it's the acceleration of the motorcycle multiplied by the time it takes for the motorcycle to reach that final velocity, right? So we have both of these terms, and we can find this time it takes for the motorcycle to go from here to here. Okay, so we do that just by solving for Tm1, that is Bm1 divided by Am1, which is 58.8 meters per second divided by 8.4 meters per second square, right? So that leads to 7 seconds. So that's something important that we have to do before actually going into the equations of xm1 and xm2. That's going to be important because eventually you'll notice it's a piece of information that we'll need, right? So going back to the motorcycle, but now for xm1, and using this second basic equation as well, we can know same thing for the motorcycle. Initial position is 0. Initial velocity goes to 0. So we know it's going to be the same thing. 1/2 of the acceleration of m1 multiplied by t square m1 for that portion of the displacement, right? So we already know that Tm1 square, it's 7 seconds, but we can also express that as the equation we got here. So if we do that, just, we cancel this square for the Am1, and we cancel this Am1 here, and we have 1/2 of Bm1 square, which is, it should be Bm1 here, which is, by the way, it's the same velocity once, because it's the final velocity divided by the Am1. I hope that does not sound confusing, right? But this is the expression that we're going to use, the equation that we are going to use for xm1. And like I said, it's just pure algebra there. It's nothing fancy to get to that point. Same thing for xm2. Same thing. We already solved then this. We already have this expressed in terms of something that we know and we can find. Now we have to do the same thing for this portion of the track. And for that, again, we're going to be using this second basic equation. And same thing goes here. X initial, it's 0. And this is a tricky one. That's something important to understand, because now we are saying now that the motorcycle, it's here. So why would the initial position would be 0? If that initial position was here, why is that now this initial position will go down to 0 as well? Well, you could actually think, because that's something that it's a valid guess, or it's a valid thought. You can think that you should take this initial position not to 0, but actually you should solve this, which you can actually do because you have the information, you have those data, those numbers here, and put that here because it's not 0. But there's I think that's kind of the tricky part of this problem. You have to remember that the initial position for xm2, it's not going to be 0, because then you would be calculating from here to here, right? And it's important to understand that the only thing you're looking for, it's starting from here to here. You want to find xm2, so this distance here, this displacement here, will require that you take this as the 0 initial position. If you do that, then if you don't do that and you take this into account, then you are adding some factor, some of the calculations that involve XM1, and you can try and see what it leads to, but the answer won't be right, because you're including part of this, right? This section here. So that's the reason why you have to make x0 equal to 0 if you're calculating this section here. Just want to disclose that, because that's one of the parts where I've seen that people gets confused a lot, and that's important to say. Okay, so that's the reason why this goes to 0. But now we have the term of initial velocity multiplied by time, and initially we made these 0. This one 0 because it was the car was moving from rest. But at this point in time, when the motorcycle is here, it's not moving at 0 speed, right? It actually has some speed. So we are going to include that. We're going to use that here, and that's why this won't be 0, okay? But then we have this other part of the equation, which before it's what we used to find XM1 here. But now we know that the acceleration, again, it's in physics, I think this is very important. You have to be, that's why I think it was important to establish this kind of drawing and the animation that I showed. That's the importance of that. It kind of helps you better understand what you're doing, and then you can start evaluating things in the right way. So that's why I said that the acceleration from here to here goes to 0. And that's the reason why this whole term here will go down to 0. So you can now know that XM2 equals BM, which is the velocity for the motorcycle, which is, by the way, the velocity it's using from here to here, multiplied by the time it takes the motorcycle reach this spot from here to here. Now that time we can say it's going to be, it could be, we could say it's TM2, but TM2, it's also equal to TC minus TM1, and that's better because we already know TM1, which is 7 seconds. So we can kind of move that away, or kind of use something that we already know. We are going to notice that when we create this equation but replace everything we already know for both XM1 and XM2, we're going to have just one piece of information missing, right? And that's exactly what I've done here. If we follow this arrow here, XE, it's going to be 1/2. That's here. XE, it's actually this, right? 1/2 of the acceleration of the car multiplied by the time it takes the car to reach that final spot, squared, right? So that's what we have here, and then that equals to XM1, which is 1/2 of BM squared divided by AM1, which is this here, XM1, plus BM, which is this expression here, BM, multiplied by the time it takes the motorcycle reach that final spot, and that's TC, which is what we're looking for, minus the 7 seconds it took for the motorcycle to go from here to here, right? So that's going to help us find TC. Now, this will lead you, as you can imagine, to a quadratic expression. It's something I'm not going to do here. I'm not going to solve it here, but I'm just going to share the results I got. That's something that you can do. If you have any questions, just let me know. I'll be more than happy to answer in my best. Do my best to answer your question or your questions. But the results I got was, as you know, any quadratic equations will have two solutions because it has both a plus and a minus sign that will lead you to two different results. And just wanted to point out that while I included both results here, only this one here, it's both results are mathematically correct. Only one result is physically meaningful and possible, and that is this. And it has to be this one because we already know that it takes 7 seconds for the motorcycle to reach XM1. So in order to reach XM2, the time cannot be less than that. So that's the reason, that's how we can know that this is the right time that we are looking for, right? So with this, we have answered the main question that we had to answer here. We can, of course, continue to solve things like, for instance, XM1 and XM2, and that's what I did here. And these are the numbers that correspond to both XM1 here, sorry, this is 0, this is XM1, and this is XM2 from here to here. And if you add those two up, you should have XC, which if you do here, it's kind of the same, it's pretty close. I got this XC number, I got it from this expression here. So it's, you know, every time in physics, this happens a lot. Since you're using decimal, you're using 4.44, 16.56, 58.x. You're using numbers that are fractions and are not exact numbers. That's what happens. So you have approximations on your results, but you know, pretty much these two numbers, 205 plus 562, will give you 667.8.9. It'll be, the difference will be very minimum. So that's the end of this video. Like I said, if you have any questions, let me know. I also invite you to pay a visit at toysandphysics.com. You'll find more interesting information there, more interesting stuff. I add new information every single day. It's a work in progress. I cannot say it's complete, but I'm doing my best to add as much information as I have so that you can find physics a bit more interesting, a bit more engaging, and hopefully you're going to be learning something. Okay, so like I said, if you have any questions, please just let me know. I'll be more than happy to know and to help you solve those questions. And that's it. Bye for now.